Hello there! In this lesson we're going to learn about refraction as it applies to lenses. And of course lenses are in all sorts of devices that we have around. This set of binoculars here, of course cameras have lenses in them. I'm not sure where this one came from. My dad had it in the garage from somewhere. But as you can see, definitely diffraction going on here. And we have some magnification of the subject behind. And we're going to look at how you can determine where an image will be from a lens of different types. So to start off with here, I want to point out that everything we're going to do here in grade 10 has to do with thin lenses. And that's because thick ones do something that the thin ones don't. A thick lens, like this one, or a thick piece of glass, say, will refract the light quite a bit because it has a greater distance between the front and the back, and then refract again. So you get two refractions that happened, and you get quite a bit of displacement of the beam of light. With a thinner lens, this displacement becomes a lot less and can be almost negligible if it's thin enough. So with a lens, rather than just a rectangular prism like these guys, you're going to have curved surfaces, and as long as the lens is thin enough, we can make predictions about where the light beams will go and where the image will fall. And so that's what we're going to focus on, is the refraction of light through thin lenses. So the first type of lens we're going to consider here is going to be a biconvex lens. That means it's convex on two sides. And so just like the mirrors, the curved mirrors, we're going to have a central point. That's going to be called the optical center. And then we can run the principal axis through the optical center. So there we go. And then if we shine some light beams through one side, we'll find that they all will converge on the other side. And the place where they converge is going to be our focal point again, or focus. So we call that F. And then, of course, because it's biconvex, that means you could do the exact same thing on the opposite side. And so that same distance on the opposite side is called the secondary focus, principal focus. And you call that F prime. So F with no like apostrophe, and F with a little apostrophe that you call prime. So just like with your curved mirrors, there are predictable things that your light rays will do when you shine them from different angles. So first off, if we shine a light ray parallel to the principal axis, like so, it will always refract as it goes through the lens through the focal point, the focus, right? So that's F here, right? And conversely, if you shine a light through the secondary principal focus, so this F prime on this side, it'll come out parallel to the principal axis. So those are two that you can use. Finally, if you shine a beam through the optical center, then you don't get any refraction at all, or the two refractions cancel each other out, as long as this is a thin enough lens. So everything we're going to do in grade 10 is all going to be thin lenses, no big thick ones, so no discernible displacement of the light beam. So if you shine through the optical center, it should come right out the other side and with the same trajectory. So let's see if we can find where the image will be, starting with an object outside of 2 times the secondary focal length. So we're going to start with a parallel ray there, which is going to bounce through the focal point. Then we'll do one through the secondary focal point. It'll come out parallel. That's enough, but we can do one more through the optical center. It goes straight on through. And so that's enough to determine where this image is going to show up. So there you go, that's our image. So now to describe this image, we'd say that the size is smaller than the object. The attitude is inverted. The location is between F and 2F. There's F and there's 2F, so in between there. And the type, you call this a real image because you could actually, if you put a piece of paper or screen of some sort at this point, you would be able to see this image projected. So this is really how a projector works. The film in the projector would be, upside down, so you put it this way, and then the projection would be right side up for the people watching the movie. Okay, next. So to move things along, we're going to pass over one of the locations. That is, if you put the object at 2 times the secondary principal focus, you will get the exact same object at 2 times the principal focus, just inverted, right? So moving on beyond that, we're going to go between the 2 F prime to the F prime area and see what happens with the image there. So light ray parallel to the principal axis through the focal point, 1 through the F prime, out parallel, and then 1 through the optical center, and we get a pretty good idea of where it should be. So we're going to have our object way out there. So if we're going to describe this one, we'll say that this time we have a bigger image than the object. The attitude is still inverted. The location is beyond 2F, and the type is still real. Alrighty. So at the secondary focal point, you're going to see something that should be familiar to you from when we did the curved mirrors. So when you're right at the secondary focal point and you shine your light ray parallel, of course it comes out through the focal point. If you go through the optical center, it's going to come out through the focal point. And so what do you think? If you're standing over here, you're trying to put a screen somewhere, these light rays aren't going to come together, which means you're not going to get an image. It doesn't matter where you move your screen or where you put your eye, no image will be able to be formed. So we don't have to worry about any of this because we're not going to get any image formed. Alrighty, so finally going to move it inside the secondary focal point, and let's see what happens with the light beams here. 1 parallel goes through the focal point, 1 through the optical center, comes out the other side. You can kind of see that these two are diverging. So we're not going to get any real images on this side. However, we know that our brains are good at projecting backwards and making it seem like that there's an image on the other side. So we're looking for a virtual image here. And if we go backwards, well, we see that the light rays converge here. And that means we're going to get some serious magnification. So this is what you would use for, a microscope or something like this that's going to enlarge the image as the light goes through the lens. So the size is going to be much larger. The attitude is the same as the object, so upright. The location is beyond 2F, and the type is virtual. The light rays don't actually come from there, but our brain assumes that they do. That's what makes it virtual. So the last thing that we're going to address here are diverging lenses. This lens here is biconcave, meaning it has 2 concave surfaces. And so light rays act a little differently when they go through these than when they go through the convex ones. So first of all, parallel light rays are going to diverge away from each other when they pass through a biconcave lens. And that means that our brains can do the work of projecting those rays backwards, and you end up with your primary focus on the same side as where the light rays are coming from. And that means the secondary focus will be the same distance over here, and so that'll be your F prime there. So for determining where images are going to be, you can always do what we just did here. You can make a parallel ray to the principal axis, and it will refract as it goes through as if it's coming from the focal point. Then if you aim a light ray at the secondary focal point, so it's the reverse, so if I aim at the secondary focal point, then it'll refract out parallel. So just the reverse of what we did on the previous type. And of course the same one, if you fire it straight at the optical center, it'll go straight on through, just like the biconvex lens. So you got 3 options there. As long as it's a thin enough lens, you can use those same principles to work out where the image will be. Alrighty, so there only is one outcome for an image from a diverging lens, similar to the diverging mirrors that we looked at. So let's put a couple of light rays on here and see what happens. So first off, we got one that's parallel. It's gonna diverge away from the focal point, right? And then we put one aimed at the secondary focal point and it'll come out parallel. So our observer's over here, and with their brain assumes that light rays travel in straight lines, so it's going to project backwards and gonna see the image at this point here. So the size of the image is definitely going to be smaller than the object. The attitude is the same, so upright. The location is closer than the original object, and the type is definitely virtual. Our brain is doing the work of finding that image. Okay, hope that was helpful. We'll talk to you soon.